Hopefully on that first one, hopefully everybody was okay with this answer and ended up with, yeah? Yay, hooray. I actually did these a little bit out of order. This last one should have come next. Is that the one I wanted to come next? Yeah. Doesn't matter. Let's do the next one. What happens on that next one? Bromine. Does it matter which carbon I put the bromine on? No. Good, because it's completely symmetric. Is this the correct answer? Oh, good. Some shaking heads no. What's wrong with it? The hydrogen can be implied, so we don't have to stress about that. So that's not why it's wrong.
There's an enantiomer.
Both of those are products. Okay. We get the enantiomer forming in this. Why? Our pi bond comes out, picks up the hydrogen. Ultimately, that's not going to matter. But what's going to matter is that we form that carbocation. Where can the bromide attack from? Either the top or the bottom. We get enantiomers. Okay. So we have to watch out for that. Why did we not worry about that in that first reaction? There's no stereocenter. There's no need to worry about wedges and dashes in that because there isn't a stereocenter. As soon as we move to that second one, we have a stereocenter. We have to watch out for it. Okay. Does that mean every single time you look at a problem you have to be thinking about it? Not necessarily. It depends on what the question's asking. If the question is just looking for, hey, did you do an addition? Cool, you've got it. Okay. If it's looking like where they're showing wedges and dashes, you should pause and think about that. Your addition reactions, all of them have this issue of enantiomers potentially coming out of it. Okay. And that's all because of that carbocation possibility, at least within this section. What happens when we move to the last one on that list? Where do we put the Cl? We'll call it position A or position B. Or does it matter? A. Why does it need to go to position A? If you look at the intermediate that forms, you're putting a carbocation either at position A or position B. Both of those are secondary. So we say, oh, okay, it's secondary, no difference. What does A have going for it? There's resonance to stabilize the carbocation. That is going to be the favored product. So when we go through and put on our chlorine, we can put on our chlorine. Do we have a stereocenter? A is still technically a stereocenter, which means we also have the enantiomer. Right, or we could just say a racemic mixture. Kind of makes sense? So remember, stability of the carbocation. Tertiary, secondary, primary is a very good first step, but you have to take into consideration that resonance effect. Make sure that evaluates through. Top one, top right. This one actually gets kind of tricky.
Can it stabilize the carbocation at the tertiary carbon?
Yes and no. I see two secondary positions, or what would soon become secondary. How did you get to the tertiary?
Because the structure will try and find stability within itself.
How? Through a rearrangement. Got a carbocation, you got to look at rearrangement. So what will end up happening is we'll end up with a big mixture of products. Initially, we've got Ooh, yeah. And a favoring for that being possible. The other possible product, and then we end up with, at this position, I'm just going to say plus or minus for the moment. The other possible product is where we would have put the chlorine here, but that would have been a secondary carbocation. Can I rearrange the secondary carbocation? Yes. I can end up doing a rearrangement to put the positive charge on our tertiary position, which ends up putting us to our final product. Right. Do I need to specify wedges and dashes on that last product? We're having a mixture of yes and no's. Okay. Why yeses?
When you do the hydride shift, though, you're losing your wedge edge.
So when we do the hydride shift, yes, we lose the you got me doing it now. The wedge and dash. Okay. So what we would end up showing in that carbocation after our shift is just that. But then the bromide, or in this case chloride, could still attack from the top or the bottom. So it could be wedged or dashed. So both are possible answers, or both are possible attacks. Is it necessary to show it? Why no? When do we show wedges and dashes? Primarily for stereocenters. Do we have a stereocenter? No. Okay, so adding that extra information of saying the chlorine is dashed and the methyl is wedged isn't wrong. It's just not useful. It's not adding anything to this. Okay, because that is not a stereocenter. The top possible product is an interesting one to talk about. You'll notice that I just wrote plus minus. Okay, I'm going to show a new notation here. That notation is going to be a squiggle. What we're saying is that that chlorine can be wedged or dashed. Let me draw that again down at the bottom of the screen. So that chlorine could either be wedged or dashed. Technically, both are possible options. If I made it wedged and then said plus an enantiomer, would I be correct? Why no? The other stereocenter does not change. Okay, so the two products we would end up with, we'd have this product and we'd have the methyl still wedged with the chlorine now dashed. What is the relationship now between those two structures? They're diastereomers. Okay. So if you see wedges and dashes in a reaction, if you have a chiral starting material, you will end up with a chiral product very likely. Okay. So watch out for that. You may be asked, what is the relationship between the products in this reaction? Okay. Questions on that one? Okay, questions on any of the ones that are, sorry, go ahead.
You say plus diastereomer?
I would probably accept that in a short answer thing. I'd say plus diastereomer. On a multiple choice exam, which is what you're looking at, they would probably say what's the relationship in the products, the major products out of this reaction. And they'd say enantiomers, diastereomers, structural isomers, something else, I don't know. Okay. And what they'd be looking for is that diastereotopic group. Any questions about the additions that have been shown? What type of additions did we do? All of these? These were acid-base reactions to start it off with, and you were saying, I think you have the right idea. Hydrohalogenation, because we're putting on a hydrogen and a halogen. Okay, so now let's clear everything. And take a look at that last question. When we looked at our hydrohalogenations, actually now I want to erase that top one. Okay, we had an acid-base reaction happen first to pick up the hydrogen, and then the bromine came on as a nucleophile. And so we ended up adding hydrogen and bromine across the double bond. Are there other atoms that could be nucleophiles? beyond halogens? Sure, good answer. What other atoms could be nucleophiles?
Water.
Be more specific than water.
OH.
Oxygen could be a nucleophile. So if we go through and take a look at water, we could just as easily have written that H, OH. What might we predict to happen if we take an alkene and we add water? Yeah, we'll put the hydrogen on one side, the OH on the other. Our alkene comes out, picks up the hydrogen, donates electrons to the oxygen. Our now negatively charged oxygen can come in and attack the positively charged carbon of our alkene. Everybody see that? Now the question, is this likely? Okay. Hearing a no, any ideas why? Push that further. That's a possibility. I didn't think of that. What do you mean by hydrogen bonding?
Hydrogen bonding is stronger than one of the dispersion forces that are
Interesting thought. I hadn't thought of that. We're saying that the hydrogen bonding within the water molecule or between water molecules is stabilizing the hydrogen and the OH to the point where they don't react. Okay. Let's push it a little bit further. If we take a look at our hydrohalogenations, what's the reactive species? The hydrogen coming from, yeah? The acid. In particular, it's not just the acid. The hydrogen coming from the strong acid. Yes, the alkene is reacting, but that's not what started the whole reaction off. What started the whole reaction off was a strong acid. The strong acid gave up H+. We need to stabilize that H+. What do we have as a source of electrons that could stabilize that? Now we bring in the alkene. Why is that a problem when we now look at the water reaction? Water is a weak acid. So if we just add water to an alkene, what do we expect to happen? Nothing. Okay. Think back to the lab we did however many weeks ago, 2 weeks ago. We did the elimination lab. One of the things that you did with that product was wash it with water. Why could we get away with washing it with water?
Because it wouldn't react.
Because it doesn't react. Okay? So if I do want to put on an alcohol, how could I possibly push this reaction in such a way that I could get the alcohol, get the alkene to react?
Strong base.
Could go through and add heat, adding a strong base. Let's consider that. So what we're doing is now adjusting that, and instead of saying it's H2O, I add in OH minus. Cool idea. We're now increasing the nucleophilicity so that can come in and attack the positive charge, right, of our intermediate. So we look at our intermediate. Got the positive charge. Let me draw it on the carbon that we've been using. So if we use a stronger nucleophile, that reaction should happen much, much faster, right? Completely agree. Is that going to facilitate this reaction?
No.
Why not?
like sodium or something.
It won't want to form the H+.
I can change the strength of this nucleophile, and that will speed like crazy the second step of the reaction.
It won't speed the slow step.
It doesn't affect the slow step. The slow step is that first one. I have to get to the carbocation first. For that to occur, does the OH do anything helpful? I've got an alkene with electrons and an OH with electrons. What happens when I bring them near each other? They repel, no reaction. So it's not a bad idea, it just unfortunately helped the wrong step. So what we're trying to do is speed this first step. What do we need to speed that step? We need an acid. We need a strong acid. So what should we go through and add? Well, strong acid. Pick one. Okay, I heard two answers. We're going to write both answers down. I heard HCl and I heard H2SO4. Okay? I'm not calling out the people that voted for these or initially put these out there. Would both of these equally work?
No.
Why the no?
Because the chlorine is more negative.
The chloride is also a nucleophile. So that if I add HCl and water, the chloride is now going to compete with water to be the nucleophile. Which is the stronger nucleophile? Chloride. And we end up doing our substitution, just like we've done before, as a hydrohalogenation. So the HCl does not work as a very good option because the chloride can act as a competing nucleophile. What about the H2SO4?
It's bigger.
The conjugate base of H2SO4 is charged, just like the chloride. So we might say, oh, red flags, it's strong. That's a problem. Is it a strong nucleophile? No, because resonance. The electrons are now stabilized into the structure. We've scattered that negative charge over a very large area, which stabilizes the sulfate, making it non-nucleophilic. So if I want to facilitate this reaction, what I can go through and do is add H2SO4. It being a nice strong acid will supply the H+, which then reacts with the alkene to get me to the carbocation. Now that I have the carbocation, now my water can come in and attack. Let's go back to the initial thought of the OH. Okay, adding hydroxide. Hydroxide is a strong nucleophile. Can I do hydroxide in this next step? No, because
It will react with the hydrogen.
it would immediately react with the sulfuric acid. Okay? So what we're doing in this reaction, I don't know, did I stepwise this nicely? Whoops, yes I did. We need H2SO4 to help with that addition reaction. Okay? So we can now do an addition with this acid-base catalyst starting at the beginning, convert our alkene into the carbocation. Once we're at the carbocation, we can have our nucleophile come in and attack. Okay? So water was a good nucleophile. I forgot what the next slide was. We'll come back to it in a second. Okay? So now what we're going to do is take a step back and look at those other reactions and the concerns. We have stereochemical traps. Okay? We have to be thinking about where the attack comes from. Sorry, that may have been a bad time to switch. Do you guys have questions back here?
Do you use hydronium as that?
It's the same thing as saying H2SO4. Yeah, it's just a question, where did you get the hydronium from? By taking water and acid. So, stereochemical traps. So we just talked about some of these issues with showing the wedges and the dashes. Okay? So we have to think about how our reaction is occurring. So what we've got on the left is what functional group? It's an alkene. How do you know it's an alkene? You make pi bonds. How do you have pi bonds? P orbitals. So what we're trying to show with this drawing is that those p orbitals are what have the electrons. Those are what are coming out and attacking. What are they reacting with at first? Strong acid. They are reacting with H+. Okay? Which of those orbitals comes out and attacks? Well, that's going to be dependent on what those groups are around it. And I intentionally left this kind of vague, probably to my detriment, but hey. Okay, so we went through and said we put the hydrogen there. Okay. We now have what kind of a structure? So we started with an alkene. We are now at what? A carbocation. How do carbocations react? Well, that's kind of a weird one. How do carbocations react? They accept electrons. Good call. Okay? So they will accept electrons from a nucleophile. So they're acting as an electrophile. Where do those electrons go? Where do all electrons go? Into orbitals. Where can we put the electrons from our nucleophile? Into the empty p orbital of our carbocation. Where does that p orbital exist? Above and below, which means our nucleophile can come in from either of those two positions. Right? What is that going to do to the stereochemistry of your product? It could very well give you enantiomers out of that product, or potentially diastereomers, depending on what you're looking at. Right? So what we've got to be careful of is when we go through and deal with our alkenes, most cases they are achiral, which means when we look at our products, plural, have to also be achiral. Right? The only way we can differentiate and get a chiral product from a chiral starting material is if we add, a chiral product from an achiral starting material, is if we add some other chiral species to mess with the reaction and force that chirality. Right? This may or may not surface as a problem. Right? So what you have to do is be aware of what answer choices are showing up, and are those answer choices really asking you to think about these stereochemical traps, or are they just letting it slide and not worrying about it? Right? So the signifiers that you're looking for, wedges and dashes. That's a big, big thing to look for. If you see wedges and dashes in your answer choices, you should pause a minute and think, okay, stereochemistry is potentially coming into this. Okay? The other thing is we can change your viewpoint on the molecule. Wedges and dashes implied specific locations of where the atoms are, but so did Newman projections. Right? So did Hayworth projections. Right? So if you see any of those kind of secondary weird configurations or ways to represent a structure, you should be careful because they're probably asking about stereochemistry, and you need to be very careful with your answer because you will likely see all sorts of possible arrangements. So watch out for those. What does a Hayworth projection look like? We briefly talked about it. These are Hayworth projections. We've taken a ring and we've kind of turned it on its side. Okay, so when we draw a ring, it's normally flat, like the iPad. If we shift to a Hayworth, all we're doing is now looking at it from the side. Okay. It's a slightly different viewpoint on it. Some people find it easier to see, some people find it harder. It's just kind of up to your perspective. Okay, so your textbook's got this nice figure. They did something a little bit different in this one. What did they change in this reaction? What type of reaction is this? Addition. Which type of addition? Hydrohalo. Hydrohalogenation means there should be a hydrogen. Where's the hydrogen? D represents deuterium, which is hydrogen. Why are they introducing deuterium into this? What they are really, really pushing for is getting you to think about those stereochemical concerns. That pi bond had electrons above and below the plane. So when we go back to the figure that we had here, we really were only concerned about the nucleophile attack. And that's because typically our hydrogen is being put on in a place that already has hydrogens, which means there's no chiral atom. But we can change things around a little bit to make sure that we end up with a chiral position at that point. That's what's happening in this case. So our pi double bond can attack the deuterium either from above or below the plane. That's going to put the deuterium relative to the ring either above or below the plane. The bromide, as our nucleophile, can then attack each of those two possible intermediates either from above or below the plane, which gets us a total of 4 possible products. But it turns out of those 4, 2 end up being the same. A is the same as D, or sorry. No, actually, we end up with 4. Because A and D are enantiomers of each other. Yes. Are they? Am I looking at that right?
Yeah.
Yeah, they're enantiomers of each other. So this drastically made this problem more complicated. right? Because we end up with these 4 possible products. And that's because we now have 2 chiral atoms coming into this. So if you got 2 chiral atoms, 4 possible products. Okay? So this is kind of the extreme version of your addition reactions, trying to draw your attention to those issues that can pop up with this. Questions when it comes to stereochemistry? The other nucleophile. So in our hydrohalogenations, okay, if we look at our product that comes out of this, we end up with what functional group as a functional group in our hydrohalogenations? What functional group? Alkyl halide is our general term. So you may hear reference to alkyl halides popping up. Okay, this kind of comes from your nomenclature. All we're saying is we have some alkyl portion. Alkyl, yeah. And we have a halide portion. More specifically, this product is an alkyl bromide. Okay? Once we have our alkyl halides, what kind of chemistry is available to us? Well, we really only get substitution and elimination. That's it. Okay? So we actually lose some of the chemistry there. We can't do any acid-base chemistry for the most part because we don't have any really acidic atoms and we don't really have any basic atoms in our alkyl halides. So we lose some functionality by changing our alkene to an alkyl halide. In the alkene, we at least had 2 carbons that were reactive. Each of the carbons of the pi bond. In our alkyl halide, we now only have 1 carbon where the halogen is attached. So we've lost some kind of reactivity to this. If we go through and do our addition reactions, okay, this is quite likely something that could potentially happen. But maybe we want a little bit more chemistry with this. This is where we can change the nucleophile. So if we look at the overall reaction that I gave you guys for additions, okay, we've got hydrogen bound to a nucleophile, and that's really what's doing your addition. So are there other nucleophiles that we could use? Well, we talked about oxygen being a possibility. What was the issue with the oxygen? What did we still need? We still needed that strong acid to get our reaction initiated. Okay. Is there another potentially nucleophilic option? Nitrogen. Nitrogen's a reasonable nucleophile. It's got that lone pair just like oxygen. Could we go through and do an addition reaction with nitrogen? Okay. Well, just like with the oxygen, we're still going to need that acid catalyst. Okay. So we've got 2 possible examples coming out here. Before you frantically write this down, we need to talk about it. The one on the left, that makes sense. We talked about that one. The acid can protonate your alkene. Water can act as a nucleophile. What's happening on the one on the right? Our acid could still protonate the alkene, and the nitrogen could still potentially come in and attack, right? Which is more basic? The nitrogen or your pi bond? Nitrogen. Your nitrogen is insanely basic, which means when we put this mixture together, these 2 first react to produce NH4 positive. Let's say I still add an excess of acid, so the acid still somehow comes in and activates this. And I have my carbocation. Do I have a nucleophile? No. Okay. We can't use our amine in acids to generate this addition reaction. It does not work well. Get horrible, horrible yields. Okay? So really all we're looking at under these acid-catalyzed conditions are your halides and your oxygen acting as a nucleophile. And that is it. Your textbook, well, do you guys have a question on that?
So it doesn't work well because it'll react more with the acid than it will with
Yeah, the amine will react with the acid preferentially. So you end up canceling out your nucleophile. And now you have no nucleophile. Without a nucleophile, you can't do the second step of the reaction.
Why does that reaction happen? Because aren't you going from a non-charged to a charged?
True. So not your charge rule doesn't always work. H2SO4 is a really strong acid, so it comes down to which can stabilize that hydrogen better. Okay. Do we want NH4 as a positive and then the oxygen with the negative? Does that balance out that oxygen sharing electrons with the hydrogen? It turns out it does. So your textbook gives you the nice big long mechanism, which we kind of alluded to for your water attack. It's the same general idea that you've been doing. Your hydrogen reacts with the alkene first. Okay? We have to get that strong acid in there. In this case, they're showing H3O+, okay, which might be an interesting question. Why are they showing H3O+ and not, say, H2SO4? What was that? This goes back to that topic way back in chapter 6, I think I was talking about. There's a leveling effect. If we're in a water solution, the strongest acid we can have is the strongest acid that water can support, which is H3O+. So when we add sulfuric acid to it, sulfuric acid is not going to be our active acid doing all of our mechanistic stuff. Really, our active acid is going to be the H3O+. Minor note, not a big deal, just in case you were thinking about that. And the next step, your nucleophilic oxygen can come in and attack that positively charged carbon. We can then lose the hydrogen to the solvent in the last step to go through and end up with our final addition product. Why did we not have OH- come in and attack? I said another way, why did I not go through and say that water lost a hydrogen to some base, I don't really care what, to form our OH-, so that the OH- can now attack that carbocation?
Because the base would be more reactive.
OH- is a strong base in an acidic solution. So that doesn't make sense as a mechanistic step to do that first. What we want to do is go through, do the nucleophilic addition first. We end up forming a strong acid, okay, as our intermediate in that step, which is okay. It's okay to have a strong acid in that step because I'm in a strongly acidic environment. That's actually fair game. Okay? So mechanistically, it makes sense. Questions on what's shown in the mechanism? Do you have other questions? Okay, well then I'll ask it. Does oxygen have to come from water? Are there other ways we can get that oxygen into this reaction? Probably, good answer. Let's pull on another oxygen source that will likely be consumed excessively at the end of this semester. And ethanol. Can that act as our oxygen source? Yeah, that oxygen has the lone pair electrons. It can possibly donate its electrons into our nucleophile. All that ends up changing, let's see if I can actually make that a little more obvious, is we would now have our CH2, CH3 at that step with our positively charged oxygen. All right, so the nucleophile is just our ethanol. Still fair game for this reaction. Right? Could I change that to some other alcohol?
You could, but it wouldn't.
I could make it methanol. Is that going to change the chemistry? Probably not. All I've done is shorten that carbon chain. What if I made that carbon chain really, really long?
It would affect.
Sorry, that's kind of sloppy, but really, really long. Would that start to affect the reaction? How? There is a possibility that that chain could wrap back around and start to block that. Right? Typically, as a straight chain, we kind of minimize and say it's going to stay away from it anyway, so it's probably not much of an effect. But what happens if I go through and I do this? Let's get rid of that hydrogen. Is this going to be problematic?
Yes.
Yeah. That should drastically slow the reaction down because I now have a sterically hindered nucleophile. Okay, so that could have a large effect on this. Okay. Would I still expect the substitution? Probably. I probably wouldn't do this reaction though because my yield is going to be a little bit lower. Okay. Is there some other constraint on the oxygen source?
It can't be basic or have a negative charge.
True, it can't have a negative charge. Okay, so we addressed that one. That's a good point. Okay, it doesn't work to have the negative charge there. Why does it not work?
Because it's acidic solution.
We're in an acidic solution, so we can't do that.
Would it have something to do with being double bonded, or?
Explore that a little further. What do you mean?
The pi bond is gonna be higher in energy, and so it would be a higher activation.
We're still looking at just the oxygen, though.
Okay.
What if I put a CH3 out there?
It would have to be like a primary.
Would that reaction work?
No.
Why does that reaction not work?
Steric hindrance.
It's worse than steric hindrance.
The carbon, it can't form anything.
Resonance.
Can't form the, whoops. Put a CH3 there. Where does that CH3 need to be? Out here. Can water come in and pull off a hydrogen to stabilize that positive charge? No. So what does that positively charged oxygen do instead?
Separate.
It takes electrons back from the bond and goes backwards. So our constraint is that we have to have what functional group as our oxygen source?
Alcohol.
Alcohols need to be our oxygen source. Okay. What will not work?
Ester. Or
Not
ketone.
quite everything else. I want a little more detail than that. What functional group? Try again.
Ketone.
So we're now, and it's not just this, it's this whole structure. What functional group do we have? There it is. It's an ether. Ethers will not work. Interesting note, what solvent have we used in a lot of our reactions? Diethyl ether. What was THF? It's in the structure in the middle there. THF is an ether. Why are we using ethers as solvents? Because they don't react very well. Okay? They are relatively neutral species that are not easy to initiate and get them to go through and do any type of reaction on. Okay? So we can start to draw parallels by looking at what things we can change within each of our structures and how does that influence things further on down the road. Okay? Questions? Oh, I know what I was trying to do here. Oh, man, sorry. Come back here. Now I gotta figure out how I step this. Okay, the other base. So what we've evaluated is our potential nucleophile reacting this. We did our acid attack, and then we've got our nucleophile changing. But we could also change the base in this reaction. Well, what was our base in our halohydrin? What reacted, what accepted a hydrogen ion? The alkene, and in particular, what part of the alkene? The pi bond. Okay. can I change to a different type of pi bond? Or a different source for that pi bond? I could switch it to a triple bond. So theoretically, we'd end up going through the exact same cycle of a reaction, and we'd end up with this product, okay, where we've removed one of the pi bonds. So we took those pi electrons, and we bonded them to our hydrogen. And then we took the electrons from our bromine, and we bonded it to the carbocation that formed. Right? So same type of reaction, except now all we're doing is reacting one pi bond. So what I want you to do with this is provide the mechanism. So now what we want to know is, should this reaction work just as well as it did with the alkene? So go through and attempt a mechanism for this reaction. Stepwise it all the way through. And if you've got questions, raise your hand. I'll come to you if you've got it. Following the same pattern. Let me draw out that HBr a little differently. Our pi electrons come out. Pick up the hydrogen. Where would I expect to place the hydrogen? Which carbon? Middle or end? Why the end? Okay, I put the carbocation in the middle of the structure. Okay, and you're saying that's more stable because? So allylic is an interesting point to bring in. It is not technically allylic. For it to be allylic, it's pi bond sigma, there's your charge. This is charge on the atom of your pi bond. Okay, so it is not allylic. It kind of falls in that secondary category, so most people would probably be acceptable with that, and then our bromide could come in, we'd end up with our product. So as a rough approximation, we might say, yeah, this seems reasonable. It's doing the exact same thing that we would expect with the alkene. Is there a problem with this intermediate? So what are you addressing? So ignore all of that. Let's look right there. And in fact, I'm going to redraw that in the middle. What type of reaction am I showing? Substitution reaction. What mechanism? SN1. Okay, we're doing it in 2 steps. Okay, we formed the carbocation, then the iodide attacked. Did this substitution work? Those of you in the lab, you can help us out. Did this substitution work? No, it does not work. It does not occur. Why does it not occur? Say that again.
You can't have a carbocation on the pi bond.
This carbocation is insanely unstable, so it never forms. If it never forms, we can't continue on with our substitution, and we ended up staying at our alkyl halide. Why does that become relevant then for the alkyne reaction? What's the very first thing that we attempt to form? The exact same carbocation. If that carbocation cannot form, can I ever make it to the product? No. Okay. So the yield for this reaction is incredibly low. You're talking 2% yields. So this reaction does not work well at all. It is highly reversible. It goes back to the alkyne almost immediately, and we end up with no real yield of our product. Okay? And that sits on that very odd-looking carbocation. Okay? That carbocation is commonly referred to as
sp2.
So we have referred to it in the lab as an sp2 carbocation. It gets another name, which you may or may not have heard. Vinylic. Okay, that is a vinylic position. Anything attached directly to the carbon of a pi bond is a vinylic position or vinylic position. Okay? So this is now completely not synthetically useful. Okay? But what if I changed my conditions around? Okay, so the what if is if I add lots and lots and lots of HBr and I give it lots and lots of time. What happens?
You get a very large.
It ends up breaking. Whoa! Apparently I didn't draw it. What? Totally thought I had drawn it. It ends up going through and reacting first to form that incredibly unstable intermediate, and some of it continues through to make the vinyl bromide, but then that pi bond reacts very, very quickly, and you end up doing 2 addition reactions. And we end up putting 2 bromines on our structure, and we've completely removed the pi bond. Right? So kind of the lesson out of this is that we can force a reaction to occur. Okay? As long as we give it lots of time and lots of highly reactive starting materials, we can force almost anything to occur. Is this a super likely reaction to run? No. The alkyne is a very versatile functional group. Very rarely would we ever try and kick it down to a dihalide. Okay? You're losing a lot of functionality there. The reference of this dihalide, if you watched that video a while ago and I said I couldn't remember what it was called, I finally looked it up. That's referred to as a geminal dihalide because your 2 halogens are attached to the same carbon. That's a geminal dihalide. We would end up with the 2 bromines on the exact same carbon. Why? When we go through and do our second addition reaction,
So the most stable.
this still picks up our H+. Not only do we have a more stable carbocation because it's secondary, but that carbocation is resonance stabilized. Okay. The little face there, I understand. Your little face is because
Is that considered resonance of the pi bond?
we'd be forming the pi bond between the bromine and the carbon. Okay. It puts the positive charge on the bromine, okay, which is not very likely, which is why that carbon is still relatively reactive. So it's that resonance structure that's really driving this reaction forward, is because we can now form that super stable carbocation if we just happen to carry our product along enough.
I was thinking that the bromine is more neutrality, so it's improving.
So yeah, it doesn't like to share those electrons, and halogens run in this gray area of being electron donating and electron withdrawing. Okay, it gets kind of obnoxious, but they do both. Okay. So what happens if we go under hydration? So take a shot at this. Okay. Work your way through it, see what you can come up with the product. So question 1, should it be high yielding?
No.
Why no? I agree. Same reason as the last one. Our very first step, we end up with that vinylic carbocation. Highly unstable, we wouldn't expect a lot of that to form. Okay. What's the next step of our reaction? Not to give you hints or anything. Oxygen attacks. Oxygen would be positively charged with the lone pair. Does it want to be positively charged? No. So it's going to seek out electrons. Where can it get those electrons from? Okay. From the immediate hydrogen next door. And we would end up with How many people said this was the answer? Okay. Not bad. Okay. If we're adding water, we're probably adding it in excess. How many of you went ahead and took it down then to this guy? Couple of good. Okay. Following the same patterns that we've been dealing with. All of that seems to make sense. Unfortunately, what is the answer?
Also do the double bond with the oxygen.
Whoa, come back here. The answer that you actually get is this. Okay. While that may look crazy different from both answers that we drew, it is actually identical. Okay, sort of. They are all very highly related to each other. Okay, and this ultimately shows up in second semester when we look at the reactivity of that functional group. What is that functional group? What was that? The carbon-oxygen double bond is a carbonyl. This is not technically a carbonyl. We can push it a little bit further. It's a ketone. Okay, because the R groups off of our carbonyl are carbons. That was kind of freaky. So that was our first product, if you will. What do we have in this product? There is no resonance. There's an alkene and an alcohol. We have an ene-all. Go all the way back to chapter 6. I think it was 6. I think it was 7. It was at the tail end of one of those chapters. It was either 5 or 6, I think. There is the keto-enol tautomerization. That structure is highly unstable. Whoops. And it ends up interconverting. I just want to get rid of those stupid circles. So we have our enol. What ends up happening under acidic solution? That picks up a hydrogen. What charge does our carbon become? Positively charged. How do we stabilize that positive? With electrons. So we might say, hey, let's bring in the water. This is how we move to that final product. Is there a closer source of electrons? The oxygen lone pairs. And we end up shifting then to this structure with our positive charge on the hydrogen, or sorry, on the oxygen. Does the oxygen want to be positively charged? No, so it steals the electrons from our hydrogen. Water or something else in our solution picks up that hydrogen, and we would end up with our final product of our ketone. Okay. This is a very common question to pop up because you're taking the chemistry that you've done with the alkene and you've now switched it around a little bit and thrown in an alkyne. And you end up with what appears to be a drastically different product. I would not be surprised at all if your answer choices included, is everybody okay with everything that's up? Can I erase it? Sounds like it's okay. If we looked at our answer choices, they would ask, for that reaction, which of these is the product? All three of those are sort of technically products. Only one of them is the major product. Okay? So be aware of that one with your chemistries when it comes through. We will talk about that reaction a lot in second semester, that keto-enol tautomerization, because you can do a lot of cool stuff with it. Okay? Questions? Okay. Oh, there it is, chapter 7. That's our keto-enol tautomerization. It's the end of chapter 7. Well, I put a question mark there. I'm not even sure it's chapter 7. But that, you should remember that figure, because that figure came directly out of that chapter. Right? So we've got a new type of reaction happening there. One of our primary issues here, though, had to do with this first question. What was our answer to that first question? we get a horrible yield of this. So if this is going to become synthetically useful, we have to actually improve that yield. How can we improve that yield? What was the slow step? The very first one, putting the hydrogen onto the alkene. How can we make that step go faster? What's that? We can try and add more of the sulfuric acid, but it's really not going to have that much of an effect. It's still not quite strong enough. Therein lies the answer. Add a stronger acid than H2SO4. Okay. Which I don't remember if I actually listed them or not. I didn't, unfortunately. Right, so you can take a look at your book. They list a whole bunch of different strong acids, triflic acid and other things like that. Okay. The other option is adding in a catalyst. That catalyst I don't want to talk about right now because it really shows up in chapter 12. Okay? So there's our overall mechanism, beginning to end with that, most of which you guys should have already predicted. Questions? Okay. What if we have more than one pi bond? Where should we put the H+? So we get two reactions here. That's an interesting question. We could try and put the hydrogen where there's more hydrogen. What are you following by that, by saying that statement? Markovnikov. What do you think my response is going to be to that suggestion? It's a bad idea. You should put the hydrogen where you end up generating the most stable carbocation. That's the pi bond you need to react. Okay. Does anybody see which pi bond then is going to be the more reactive one on the left?
The first from the left.
There are some questions. So if you have a question, what should you do?
Draw it out.
Draw them all out and see what the result is. Okay. So now that you've got them all drawn out, we want to try and evaluate of those, where would we prefer to have the carbocation? Which of those generates the most stable carbocation? The top left, because we have tertiary, whereas the one next to it is secondary, the one immediately below that. I think you're saying that one's secondary, and the one immediately below or next to that one, primary. So we would expect our addition reaction to occur from that intermediate, because we formed the most stable carbocation. So that's how that one should propagate out. Which means if we only add one equivalent, only one addition happens. If we add a second equivalent, we can react to the other one. What happens with the second question, or the second problem? Why does that one get slightly more challenging?
It's symmetric.
What's that?
It's symmetric.
It is symmetric. Right, which actually makes things easier. If it's symmetric, does it matter which pi bond you react? No. So that actually makes things a little bit easier. And we could go through and look at our products. We end up with two possible products. Okay. Which one should react? Why the left? You form a secondary carbocation over a primary. What is tricky about that secondary carbocation?
Resonant? No.
It is allylic. There is resonance stabilizing that, which would suggest that that was an even better place to deal with our hydrogen. Okay? But what's the problem? It's not technically a primary carbocation, it is primary allylic, which is absolutely allowed to form. So I'm now comparing a secondary allylic to a primary allylic, both of which are incredibly stable, both of which are likely to form, which means what happens in the next step? I could potentially get both of those carrying forwards to the next product.
So then does it depend on the...
So this is now going to depend on evaluating kinetics versus thermodynamics. So if we have more than one pi bond, we have to start thinking a little bit more carefully with what's happening. What is our primary difference between A and B? So we do have a symmetry versus unsymmetry, but that's not actually going to be our answer on this. B has conjugated pi bonds, which means resonance. We have a resonance contribution. So if resonance is popping in, we now have to think a little bit more carefully about how our pi bonds are going to react and what possible products come out of this. Okay? So when we start with our addition reactions, we still look at putting that first hydrogen on, and we want to put that first hydrogen on such that we make the most stable carbocation every single time. Okay? After that, we then start to have to refine our method for interpretations. Okay? So the issue that comes up is that now that we've got this, we now have a resonance contributor. Okay? So, whoops. No, I did want to give you all this. Okay? Now that we've got our conjugated alkene, if we go through and run the reaction, in that very first step, we're doing the addition. We've added our hydrogen. We form the carbocation that has resonance stabilization, so both of those intermediates show up. So the bromide can either attack here, or the bromide could attack here, giving us two possible products. Are those products identical? No, they are different products. So now I have to be careful and decide, well, which of these is the correct product to draw? And what becomes challenging for this is that both are major products depending on what conditions you use. What are those conditions? Well, one is kinetic, one is thermodynamic. How are you going to decide which one's which? Draw the energy diagram. Okay? And because I think we should get some more points in on our quizzes, enough. For our purple one, we're starting somewhere intermediate in energy, and I'm moving to an intermediate with a secondary carbocation. So I'll draw it as higher in energy, and then my final product has one less pi bond, so it should be lower in energy than my starting material. For the red one, I'm starting at the exact same starting material, but I'm now going to a primary carbocation. The primary carbocation is higher in energy than my secondary, so I need to show it a little bit higher up. If I now look to my product, okay, my product should again be lower in energy than where I started, but now the question is, where is it relative to the purple one? Well, what's the difference in energy between those products? What am I focusing on? Got to find the highest energy thing within those structures. The highest energy thing between those two structures is the pi bond. Which of those pi bonds is more stable? The bottom one, because it is more substituted. If it is more stable, its energy is lower. Now I can go through and connect all my little lines really, really quickly. That was kind of awfully done, but it's close enough. What are our conditions coming at? Kinetic versus thermodynamic. If I run at ridiculously cold temperatures, how much energy would I have? Lot or little? Very little. If I'm now at very low temperatures, very few molecules are going to be able to move up, which means which product do I expect? I'm going to expect the purple product because I now have a very small amount of energy. I can't clear that activation barrier to get over the red one. If I now add tons of heat, what now happens? Now I'm going to look at the most stable product, lowest energy product. Lowest energy product is your thermodynamic. Your lowest energy intermediate is your kinetic, or what your lowest energy intermediate leads to is your kinetic product. That's your difference between kinetic and thermodynamic. I know we are done. Go ahead and pack up. I'm not going to say a whole lot about this. Isoprenes are a phenomenally interesting functional group that shows up in biochemistry. Virtually all steroids, lipids, things like that are made from the isoprene functional unit. The isoprene very commonly has two double bonds within it. It is used as your fundamental building block by doing multiple addition reactions of multiple isoprene units together to go through and make all sorts of other functional, or all sorts of other molecules. For instance, limonene, which we isolated in lab, is actually a combination of two isoprene units, biologically synthesized and combined. Right? So that part of the chapter is kind of neat, but you won't get tested on it.